Under the theme of basic heat load calculation for air conditioning system, I will explain the basis of heat load calculation. The contents I will explain are shown on the slide. If you plan and design air conditioning system for buildings, it is basic to know heat load for air conditioning. For air conditioning load, the heat load to be taken into account are air conditioning cooling load and air conditioning heating load. Air conditioning cooling load include cooling load and dehumidification load. Heating load include air conditioning heating load and humidification load. After calculating such thermal load, we will determine the device capacities of air conditioners and heat source facilities. Generally, heat load, there are various categories. That is, thermal room load, system load, heat source load, and others. The heat extraction and heating capacity to be kept at a constant temperature and relative humidity in a room are called thermal room load. Thermal room load include heat gains or heat losses and storage heat load for buildings. Let's think of heat load caused by cooling. The solar energy flows into rooms through window panes. If you consider the moment when it flows in, the load caused by the energy is equal to the heat gain. However, all of the energy does not always act as load in the rooms. Some of it is absorbed into and accumulated in the building construction frameworks. After some delay, another part of it acts as room heat load. For intermittent air conditioning, room temperature changes if air conditioners are turned off. Pickup load and pull-down load are added to the heat load when the air conditioners are restarted. This time, we will determine heat gains and heat losses. In addition, how system loads and heat source loads are related to heat loads is shown on the slide. A drawing showing a room heat gain to be cooled is shown on the slide. The heat from the sun enters the room through walls. The heat comes in from outer wall portions including roofs and windows facing the outdoor air. Such heat is one element of the heat transfer load. The solar energy from the sun comes into the room through the window panes. This is the solar load. In the room, the body temperature is higher than the room temperature, so the heat generated by a person also acts as a heat load. In addition, heat is generated by lighting equipment and office appliances. The outdoor air coming in through the gaps in the sash of the window and the door at the entrance may also cause loads. They are called person load, lighting load, equipment heat load, and draft air load, respectively. Through air conditioning, the temperature of the ground is lower than the room temperature. Therefore, the heat escapes through the earth floor in the basement walls not shown in the drawing. Escaped heat is a factor in causing heat loss. Air conditioning load for buildings include heat transfer load and solar load. The heat is transferred by three methods, namely heat transfer, heat convection, and heat radiation. The solar energy penetrates objects such as the glass window and comes into the room. Some of it is reflected away, and some of it is directly absorbed into construction frameworks. Furthermore, the solar energy is absorbed into the room by heat transfer. The heat conveyed by heat transfer and the radiation heat absorbed directly into construction frameworks are conveyed into the room by heat convection. Depending on the position of the sun, heat transfer loads and solar heat load change. Therefore, calculate air conditioning cooling load based on the direction of the walls and windows and specific time intervals. Under air conditioning, the temperature of the ground is lower than the room temperature. The heat escaping through the earth's floor in the basement walls not shown in the drawing is a factor in heat loss. The escaped heat acts advantageously for the room during air conditioning, so it is not considered as a heat load. During heating, however, it is considered as a heat load. During heating in winter, however, the solar energy acts advantageously for heating, so it is considered as a heat load. Heat load generated in the room include people load, lighting load, and equipment heat load. Those load are factors in heat gain. So, we consider them only cooling load. People load includes sensible heat load caused by heat generated by people and latent heat load caused by sweat and expiration. The quantity of the load caused by a person depends on the modes of operation and room temperature. The combined heat of sensible heat and latent heat depends on the type of work, but it remains the same in the room temperature. If the room temperature rises, the latent heat also rises due to the increase of sweat. Based on the type and wattage of lighting equipment, determine the lighting load. Generally, load caused by room appliances and manufacturing equipment are only sensible heat load. You should, however, notice that latent load may occur. Such examples include the case where cooking appliances in the room produce steam. If you calculate the heat generated by manufacturing equipment, consider factors including the electric capacity and the operating ratio of the device. Let's determine the heat transfer load. Determine the coefficient of overall heat transfer based on the characteristics and thicknesses of the materials in the construction framework. Determine the heat transfer load of the construction framework by using the result. A method to determine the coefficient of overall heat transfer factor is shown on the slide. You can determine the heat transfer load of the construction framework by using the determined coefficient of overall heat transfer factor, the square area of the target portions, and the temperature difference of delta T. The temperature difference delta T is used in two cases. It is used when the heat transfer load caused by outer walls is considered during air conditioning. Use the equivalent temperature difference. Effects of the sunlight and delay due to the heat accumulation are also considered. Otherwise, use the temperature difference between that of the outdoors or the next room and that of the target room, if the next room is not air-conditioned. In general, the temperature between the outdoor temperature and the indoor temperature should be considered the temperature of the next room. Let's determine the heat transfer load of a cubic building surrounded by walls as shown in the drawing. The thickness of the walls consists of, in order, 20 millimeters of mortar, 100 millimeters of concrete, 50 millimeters of glass wool insulation material, 20 millimeters of mortar from the outermost point of the wall. This building has 6 walls having the same structure. The overall heat transfer coefficient is 0.69 watt per Kelvin per square meter. The total area of all the walls is 6 square meters. If the room temperature is 26 degrees Celsius while the outdoor temperature is -4 degrees Celsius, the heat transfer load of the construction framework is 124 watt. So, the heat transfer load can be reduced with the use of a material having a low thermal conductivity or thicker member. The heat coming through glass windows into the room is divided into the heat directly penetrating the glass, the heat carried into the room by convection, and heat radiation after the glass was warmed following through absorption into the glass, and the conduction heat caused by the temperature difference between the inside and the outside of the room. I have already explained the heat of transmission caused by the temperature difference between the inside and the outside of the room. So, here, I will explain how to calculate the load caused by the heat directly penetrating glass and the load caused by solar radiation. Multiply the area of the window by the solar radiation heat load through the window and the shading coefficient. Calculate using the conditions shown in the drawing. The window faces the south. The area of the windows is 0.5 square meter. In Tokyo at 12 o'clock, the standard solar gain of a window is 180 watt per square meter. The glass is transparent. The thickness of the glass is 3 millimeters. Since neutral-colored window shades are used, select 0.66 for the shading coefficient of the window area. You will get 59.4 watt as the solar load. The people load is the sum of the sensible heat load and the latent load. The sensible heat load and the latent load are determined respectively by multiplying the people load caused per people by the number of people in space. The number of people in the room is often uncertain. Determine, therefore, the number by referring to the table. Suppose that the area of an office is 100 square meters while the room temperature is 26 degrees Celsius. Calculate the sensible heat and latent heat. An office building is assumed. So, for the number of people in the room, select 0.15 people per square meter. Use the number for calculation. You will obtain 15 people when you multiply the area by the number. Generally, the numerical strength is expressed as an integer. Continue calculating by using 65 watt of sensible heat generated by a people and 65 watt of latent heat generated by a people. The number of people is 15. You will obtain 975 watt of sensible heat quantity and 975 watt of latent heat quality. Therefore, the people load or total heat is 1950 watt. Based on the power consumption, calculate the heat load caused by lighting. If the power consumption is uncertain, see relevant data such as the table shown on the slide. Based on the purpose of use of appliances and equipment, calculate heat quantities generated by them. For recent offices, you should consider office automation. You should therefore expect 15 to 30 watt of consumption power per square meter. Whenever copy machines and large-sized office appliances are installed, the heat generated by them is expected as load. Take the load factor corresponding to them into consideration. Note that if you do not assume real load, Even if you calculate the heat generated by the process equipment in the factor, expected results may be very different from the real load. Additionally, there is a draft load. If systems including all air-type air conditioning systems and fan coil unit systems are used with ducts installed, and if you can expect that the pressure in the room will be kept positive, you can ignore this load. In addition, for highly airproofed buildings, you can often ignore the draft of floors without entrances facing the fresh air. However, in places including cold districts, if the temperature difference between the inside and outside of the room is large, or if systems are used in a district where it is very windy, you must consider the draft. The load of the drafts is the total load of the sensible heat load and the latent load. Based on the draft flow rate and conditions of the air, determine the loads. Look at the table where draft flow rates of aluminum sashes are shown as an example to determine a draft flow rate. Multiply the area of the sash facing the outer wall by the corresponding draft flow rate per unit. For the design wind velocity, use data provided by organizations including meteorological observatories and local municipal entities. For the draft coming in from the door in contact with fresh air, determine the air flow rate by using the air change method. In the summer, if the wind hits the entrance, expect the draft of the quantity to be twice as large as the cubic capacity of the room per 1 hour. If not, expect the draft quantity to be the same as the cubic capacity of the room per 1 hour. In the winter, if the wind hits the entrance, expect the draft of the quantity to be 3 to 4 times as large as the cubic capacity of the room per 1 hour. If not, expect the draft quantity to be 1 to 2 times as large as the cubic capacity of the room per 1 hour. This is the end of explanation of basic heat load calculation for air conditioning system.